So my name is Dr. Donforth. Thanks for coming up all the way from Edmunds to see some of the demonstrations we have. We have a bunch of different toys that I'd like to show you, do some different things. And I understand from talking with your teacher, you guys are working on motion, things moving. You just used some of the air tracks that we gave to your school a couple years ago. And so I've got a pretty straightforward little thing we're going to start with. Ball, what does a ball do if it's on a hill? Rolls down the hill. All right. So I've got two tracks here and two balls, and I can release these balls at the same time. So they'll roll down the hill, and then they'll go. We're going to have a race. Which ball do you think is going to reach the far end first? Think about it for a second silently. Think about it silently for a moment. Everybody gets to form their own opinion. Who thinks the green ball on that straight shot is going to go faster? Raise your hand if you want to vote for the green ball. All right. And who thinks the yellow ball is going to go faster? All right, there's some disagreement there. There's some disagreement between the yellow ball and the green ball. The great thing about physics is it's an experimental science. We can do the experiment and figure out what's going on. But let's hear some of the ideas. So somebody who voted for green ball. Why do you think the green ball is going to make it there first?
Well, because it's not going up something.
Doesn't have to go up to it. It's just going down, running across. All right, straight shot. Yellow. Did you vote for the yellow ball? Yellow ball. Who thought the yellow ball? There. Defend the yellow ball for me. What do you think? You're not sure why? You just think the yellow ball looks faster? Okay, so the yellow is just faster than green.
You know, I think of it as like sledding. If I were on a sledding hill, which hill would I want to be on?
Which one would you want to do? All right. Shall we give it a shot? Shall we do the experiment? Remember what you thought, and then try and verify that with the experiment. All right, so there was the idea, maybe the yellow ball is faster. Should I switch the balls and try again?
Yeah.
So now we're going to put the green ball on that track and the yellow ball on the back track. So if it was the yellow ball being faster, we'd expect the yellow to get there first, yeah?
The green one's going to get there first.
Now, what's that?
The green one's going to get there first.
Yeah.
This time? Yeah. So some people are saying it's the track, some people are saying maybe it's the ball. That's an interesting question. Are they the same weight? Yes. Would it matter? That's another experiment. So any experiment you do naturally leads into other experiments.
Also, the one that stands on it has a different.
Oh, it's a little bit different angle at the very end. Yeah, the track's gotten back. Shall we do just this experiment?
Yeah. Are they the same weight? Yeah.
That was a question we had earlier. They are. Different weights would be another experiment. All right. So the track, independent of the ball, the track makes it go faster. So what happens? They both started to speed up, and then they both ran through a straight part of the track. But then one of them got to go downhill, and as we know in Vermont from sledding, going downhill speeds things up a bit for you. So it's going faster, and then that straight path it gets to go faster as a result. And so even though it's traveling a little extra distance, it's got that down and then that uphill, that extra speed it picked up helps it get there first. Now we've got different balls, another track, so there's two grooves here, and the tracks are the same. What happens if I release two balls at the same time, identical balls, identical track? What do we expect to have happen down at the other end? Who thinks it's going to be a tie? Pretty confident in that? All right. Let's check. Now it's easier to hear, so you actually listen for the click as they hit that brass plate. Released at the same time from the same spot. What if I release them a little higher up? Still a tie? All right. Now what about if I release them at different points, so one of them is a little bit lower, one of them is a little bit higher. If I manage to release them at the same time, who thinks the lower down one is going to be faster because it doesn't have to go as far?
It's closer.
It's closer.
Go with that.
What about the higher up one? Who think? Some of you think the higher up one's going to be faster. Anyone else think something else is going to happen?
It's higher up and it's more time.
They're going to tie again. Who? So we got 1 vote for tie, 3, 4 votes for tie. All right, we ready? Ready? Set. So
No. Do that again.
Do that again.
That was just one of those magic
There's
tricks.
some sleight of
all
hand.
right, maybe I didn't do enough. I need to lift one up really high and one really low.
No.
Ready? Set. Or maybe one just a little tiny bit, and the other one, I mean, surely this one will get there first, right? Look at how far it has to. I dropped them on the same track. Operator error. So, no matter where we drop it on this curve, they hit at the same time. And this is a carefully designed curve so that the push it gets going down the hill depends on where it is. And so if it starts further away, it goes faster, it comes down, and it makes up that extra distance. That won't work on every curve. If we had a straight ramp, if I dropped one here and one here, this one would get there first. But this particular type of curve, you can do tricks where you end up getting an equal time track. So this is why we do analysis of things. So the thing that's pulling the ball down the hill, what pulls the ball down the hill? Gravity. Hopefully you've done a little bit of studying about gravity. So if I have a ruler stick, a meter stick on my finger, and I don't actively try and balance it, what's going to happen? It falls. All right. But what if instead of holding it at the bottom, what if I hold it on the top? Fall. What if I displace it a little bit? Does gravity still pull down? What happens?
Well, it'll fall sideways.
Fall sideways, and then
It'll like land sideways.
land sideways. I'm going to keep holding on though.
Oh, if you keep pulling off, then it'll stay there.
It'll stay in the middle.
No, it'll swing.
It'll swing. What do we call this?
Motion. Time.
Motion. This is a pendulum. Any of you ever have a grandfather clock or a big clock with a ticking swing? Some of you might have this. So we use this repeated motion as a way of keeping time. For centuries, humans use this as a way of keeping track of time because it's predictable. Rather than just having a ball go down the track once, you can have something that swings back and forth and it marks off time. But what swings and how it swings ends up affecting the time it takes. So I've got a series of pendulums here. Balls on strings, and if I let them both go at the same time, they both swing, but do they take an equal amount of time to swing? So they started in phase, we started them at the same time, but then they move out of phase. So one's going forward while the other one's going back, and then they come back into phase. And the different length changes how long it takes for the pendulum to swing. Here we have two pendulums of exactly the same length. What do we think is going to happen if I swing these two? Swing back and forth with the same. So I'll start them the same. And now we've got two swinging in tandem, and they stay in tandem. They're at the same frequency. What about if I start them at the same time, but I give one of them a bigger amplitude? So on this track, that one caught up because it had a bigger curve to kind of go faster. What do you think? Is this one going to be faster? Or is this going to stay the same? Is this one going to be slower? Time? Stay the same. Who thinks stay the same? Who thinks the one with a bigger amplitude will go faster?
That's the one that's farther up.
So
right?
I'll pull the yellow one farther back. It has a bigger amplitude. Who thinks that one's going to be faster? Who thinks the green one's going to be faster because it doesn't have to go as far? All sorts of options. Let's do the experiment. So I'll give one a big amplitude and one a small amplitude. Do they stay in synced? Or is one, oh, now one's going forward while the other one's going back. So one of them is faster than the other. One's going a little sideways. Try it again with a clean release. So the amplitude, how much it oscillates with a simple pendulum, shifts. And this is why when you have a big grandfather clock or a big clock tower, you try and get something that has a very small amplitude for its oscillation. The oscillation is another way of saying swinging back and forth. Now, there's only so much energy that we put in one of these things. So when it swings, it has a certain amount of, we call it potential energy, the energy from being up high, and then it gets kinetic energy, the energy of moving, and then it goes back to potential energy. So if I hold this right up in my beard and then let it go, am I going to get a billiard ball right to my chin?
No.
Will my mighty beard protect me?
No.
Conservation of energy will protect me. So the energy goes into potential energy. When it comes back, it can only go the same height because that's how much energy it had. So as long as I don't push it, I won't get hit when I do this. Also, I have a beard. And beards are great for protecting you.
A little bit cushion.
All right. So now we know that amplitude can affect how something oscillates. And in this case, the length of the string can affect how something oscillates. So I've got one thing that can oscillate here. I've got a big, heavy bar. And then it's connected to all these different things. So if I start twisting this bar, what do we expect to happen to the ball? Are they all going to swing? Because we're twisting the attachment point? Let's give it a shot. So we talk about driving something in resonance. The bottom ball, which has the closest period, the closest time it takes to swing back and forth, is driven much more effectively at this rate than the other ones. The other ones are wiggling a little bit, but it's really that bottom one that starts to wiggle a lot. What if I change this length? What do you think is going to happen now? So we've got A, B, C, D, E, or F. If I start this oscillating, A, B, C, D, E, F, E. Do we have a vote for G, I heard? All right. So let's give it a shot. We can do the experiment. We're going to set this oscillating and then see which one of these starts swinging as a result. Now they all pick up a little bit of wiggle. It actually ended up being D more than E. And that's because a physical pendulum, which is to say not just a string and a mass, but a rod that has some additional mass, changes the effective length. So there's additional corrections that you can calculate for. Now, we ended up with D oscillating in that case. We've got another pendulum here, and I'm just going to show one kind of thing in terms of being aware of physical constraints. In this case, you can have a big amplitude, which is useful because it'll swing for a long time, but you have a carefully engineered curve here that changes the length of the string depending on how much it swings. So for really fancy clocks, if you look at their pendulum, there might actually be a curve at the top to kind of change that to keep the period constant, independent of the different amplitudes that it's going to run through.
Does the string touch the little mellow curvy thing?
Yeah.
Oh, it does?
You can see the string. Let me turn it a little bit to the other group there.
Oh, okay.
All right. Any musicians in this crowd? Folks who play music?
Oh.
All right.
Everyone.
Awesome. Great. So, any of you ever worked with an actual physical metronome? Some of you. So, these are designed to use the motion of a pendulum to keep time. So it's set to tick. And this one is going about 200 beats every minute. And I've got these both set to the same frequency. So we'd expect them to stay together. It does look a little like windshield wipers. But when you have something oscillating, if it's not quite exactly in phase, now they're starting up. One's maybe a little bit faster, and so they stop looking like windshield wipers, and then they start coming out of sync. So because they're oscillating at slightly different rates, they go in and out of synchronization. Now they're back in synchronization, and you can hear them ticking at the same point. We call that moving in and out of phase a beat frequency. But we're going to get a little bit fancier. If I take just one metronome and put it on a platform that can move, you'll notice the platform wiggles just a little bit. So as the metronome, which is another pendulum, swings, it makes the platform swing. So if I wiggle the platform it's on, I can mess with the metronome. It's not very kind of me to do that to the metronome, but for the sake of science, we'll wiggle it a little bit. So we saw that the two metronomes weren't quite in sync, and we saw that a wiggle can shift how the metronome keeps time. So what do we expect to have happen if I have two metronomes and I'm going to put them on the same platform? Yeah, in the striped shirt? So you think they'll go in sync. Now before they went in sync and then they went back out of sync. Will they go back out of sync?
No.
No. Shall we give it a shot? And it takes a little time. Sometimes science takes a little bit of time.
They're like perfect right now.
So there's two different ways that this can go. When they swing in opposite, neither one of them pushes the pendulum. So if one of them pushes the platform. So if they get out of sync, and perfectly out of sync, they can actually lock into out of sync. And now it starts to move a little bit again. And that wiggle will try and push them back into sync. And it can take a little bit of time because it's a slight shift, but now they're in sync and the platform is wiggling to try and keep them in sync. All right. Now, there's lots of different ways that things can oscillate. You can have a pendulum that swings back and forth. You can have something on a spring that bounces up and down. You could have something that twists as an oscillation. Any sort of repeated motion is an oscillation. And in this case, this is a special type of pendulum that's designed to couple different oscillations. So I started moving just up and down. I've got a spring, it stretches the spring,
Spinning though.
but then some of you have noticed it's starting to spin. And so the energy of that up and down motion, it started with potential, it moves through kinetic, and then it's potential energy again. Now it's going into spinning back and forth as it twists the spring. So the spring is getting wound this way instead of stretched. But is it still spinning as much?
Now it's bouncing more though.
Now it's bouncing more again. So this actually moves back and forth from bouncing to spinning. It's called a Wilberforce pendulum. Barely any spin now, back to bouncing. And it'll oscillate between those modes of oscillation. So something as simple as just a mass, just a chunk of metal on a spring that you would expect predictable motion to happen, can have a bunch of different varieties of motion. Now we did an example with a ruler where it just swung back and forth. And often people say, well, why do you make things in physics so simple? Why have just one ruler? What's wrong? Why can't we have a more elaborate setup? So we're going to get twice as complicated. We're going to have two sticks. I've got one stick attached to a pivot point. I've got another stick attached to a pivot point. It's just two sticks. So we should get some sort of slightly more elaborate oscillation. But if I start this one swinging, it'll start pretty straightforward. But then the motion gets chaotic. That's the phrase we use for that type of pendulum. It's a chaotic pendulum.
You got to do that again. Just because we like chaos.
You guys like chaos?
Yeah. Cool.
So in the big amplitude regime, it's pretty straightforward. It's just moving kind of as one big unit. But then when that little one starts to swing around on its own, suddenly that period, that oscillation is not nearly as predictable. All right, one more time.
You know, when you do that, remember when we were talking about energy and how it transfers to one to another? It kind of is like the energy gets transferred to the little blue one, and it ends up going really fast, sort of using up that energy that's left. So maybe it's using it in a different way.
All right. Can I borrow you?
Yeah. One per.
Oh, I never heard. Well, don't answer that. So we can also have other things that help us see oscillations, that help us see wiggles. So teacher is going to kindly hold that, and I can send a wiggle down this slinky. This is a slinky. It's a special science slinky. And you can see the pulse that I send down comes back to me, and it actually inverts off your teacher. Your teacher's an inverter.
So
I can also send
when you say invert, you mean that when it comes to me it's low and then it leaves high?
What do you think? Is that accurate? So I'm
I can't see it so well.
I'm going to pull down on my side, and then what's it like when it comes back to me after it's bounced off your teacher? You see the up
Is that
all
what
the way
it's doing?
back?
Okay. Oh wow. If you do this too hard, I'm going to lift off the ground and be like, well, ragdoll.
So we call this a transverse wave because it's perpendicular. It's not in the direction of motion. I can also have a wave that actually goes along the slinky. It's a little harder to see, but I'm going to compress a bunch and then let it go, and you can see a little pulse traveling. And anyone who studies earthquakes, I grew up in California, so that's near and dear to me. There's different types of waves that can go through even the earth. We call them S waves and P waves. And you can time how fast they go and then learn about where the waves started from based on their different speeds. So if I do lots of pulses, if I kind of keep wiggling one side of this slinky, all of those waves, even though I make a little wiggle here, I get a bigger amplitude in the middle because those waves, those bounces, keep adding to each other. So we call this a standing wave, because it's kind of standing in place. And if I go faster, I can get a different shape. Anybody do jump rope? Double dutch? Try and get two loops. So here's maybe the easy jump rope, although I'm just going up and down instead of around. If I go a little bit faster, we can get the 2, and then even faster, I can get 3. So I am going to get 4, but I'm not going to use this slinky. This flyer is functionally a slinky. So we're going to use a couple different aspects of physics. We're going to use electricity and magnetism. I've got a big magnet here. I'm sending a current, and I'm going to use that combination of the current and the magnet to set up a vibration. So I'm making a little tiny wiggle here that adds to a big wiggle, and we have that standing wave. Now if you kind of listen, you'll hear things are rattling at the frequency, and this is about 20 hertz, 20 oscillations every second. If I speed it up, so now I'm wiggling it at about 30 times every second. Do I get an oscillation? Just a little tiny one. So we talk about the resonant frequency, driving something at the frequency that it wants to vibrate. And now if I go a little bit higher, we started at 20 hertz. What might be a good number to check? 50? 700?
700. Over 9,000. It's over 9. What's it? 5.
What do you notice now? Now I'm not getting any motion in the middle, but I am getting motion in the ends.
Oh, it's so pretty.
So you can barely see the motion here. I'll tell you this number, I was oscillating at 20 hertz before, now I'm oscillating at 40 hertz. What's the next number you think I should check? 60.
How many bumps does it have?
So now I've got a bump, a stationary part, another bump, a stationary part, and another bump. And if everybody's quiet, do you hear that hum? That's 60 hertz. Let's go up to 80. Slightly higher pitch. Bump, stationary, bump, stationary, bump, stationary, bump. So we can add, they're called overtones.
What would happen if you touched it? Yeah.
You want me to touch it?
Yeah. Oh, okay.
You stop it.
I stop it.
Touch it from the side.
All right, I'm going to go back down to 20 hertz, and we're going to look at this in a different way. So we're going back to the fundamental, going through the different periods of oscillation. And you'll hear everything start to rattle when I get close.
Now touch it. Touch it.
That's at 20 again?
So there's the fundamental.
Touch it.
I'll touch. So if I touch it, I just stop the oscillation.
Just like a guitar string.
I wish you did something.
Now, if I touch it at a node, at a place that's not vibrating, it doesn't actually affect it because that part's not moving.
What?
But what I'd like to do...
Diana!
So, How many wires do you see right now? Some of you see 2, some of you see 3. It's the same wire. It's the same wire, but it's oscillating at a rate, and we're looking at it. The flash of that strobe is at different rates, and that means that we see the wire only in some positions.
They're not moving, right?
So if we look at the wire, at exactly twice the rate, we see it at the top and the bottom, and it doesn't seem to move. Can you go down to just above the fundamentals? So the wire's still vibrating.
Wait, you didn't change the speed or anything, just the light.
Just the light. So I'm going to turn the room lights back on for a second so you can see. So the wire's still vibrating. But because we're only looking at it when the light flashes,
But the wire is like wiggling slowly.
all right. We are almost out of time, and there's one more thing. There's one more thing we want to do for you, and it takes a little bit of time.
This is a new toy.
So, I will add, just as a final thing while Dave gets set up, I was in school until 24th grade. I got a PhD in physics. Took me a little while, but I had a lot of fun doing it.
Wait a second, Luke, back up. So, you went to 6th grade,
I went to 6th grade,
then you went to 12th grade.
then I graduated high school,
Okay,
and then I went to college, 4 years of college, and I got a bachelor's degree.
okay.
So if high school was 12th grade, then 4 years of college was 16th grade. And then I went for another 8 years to get a doctorate's degree, a PhD in physics. So I went to 24th grade. And the longer that I stayed in school, the better the toys I got to play with. Because they just keep getting cooler. All right, is this one ready? So we're going to come back now to just simple pendulums, where we know that the period, the oscillation of the pendulum, depends on the length, and we have a bunch of different lengths. So now we just expect all of these different pendulums to oscillate, to go back and forth at different rates. So we're loading it up, and we're going to release them all at the same time.
Oh, wow.
Oh, that's chaos.
No, why? That's so unfair. Hey, there's two that are the same.
There we go.
Right back where we started again.
And it will keep,
And then it'll keep going.
it'll do that whole thing again.
Yeah, it's a little out of adjustment, so they're going to get a little bit out of phase. But
So we carefully tune each pendulum, each oscillator. Let it keep running. We carefully tune them so that there's a ratio between the different periods, which means everything will slowly move out of phase and then come back in phase. It's the same as the metronomes 13 times over. And it'll move in and out of pairs and all of those different sequences that you can see. All right? So something as simple as just a mass, a ball, hanging on a string, swinging back and forth, can illustrate all of these different beautiful concepts, get chaotic, come back in synchronization, and be a beautiful pattern. So thank you very much for coming up and spending part of your morning with us. Thank you.
That's just too much. What if we put that on both hands and we wiggle at the same time?
It would probably mess up the overall rotation, but not bring it to phase. The Coca-Cola thing has got to be pretty close to start.